Hello everyone, I'm excited to present you next our VR walking excavator simulator project. This work is brought to you by Cheng, Gilberto, Mazzola, Samuel Knüsel, Michael Schreiner, and Andreas Kunz. I'm a PhD student at Innovation Center Virtual Reality at ETH Zurich and a scientific assistant at RhySearch. This project is a joint research collaboration between ETH Zurich and RhySearch in Switzerland. So first, in this project, we built to the best of our knowledge the first VR simulator for a walking excavator. And a walking excavator is a specialized machine used on steep and uneven terrain, for example, in the Swiss Alps. And it is featured by a unique capability of climbing by coordinating the four legs with the machine arm. And this capability comes with a major challenge, which is the complex control. The operators may control up to 20 axes at the same time using specialized joysticks and foot pedals. And training can also be risky that instructors often need to stand at the cabin doorway to intervene with the door open, which exposes them also to hazards. And those challenges make a training simulator necessary. So in our work together with a walking excavator manufacturer, we implemented a VR-based simulator for walking excavator. And with this prototype, we conducted two user studies, the one on the impact of visual perspectives and the one exploring passthrough to support learning in the simulator. So for related work, previous systems have used motion platforms and desktop screen setups for teleoperation and training. However, here we see screens only provide a limited field of view, which makes it harder to look around, especially for tasks like rear leg observation. Related work also studied how visual perspective affects robot control. Results suggest a trade-off. First-person view would increase realism, while a third-person view improves environmental awareness and can support more efficient movement. The key limitation in these studies is that the participants repeat similar tasks under multiple conditions, which can introduce learning effects. And these insights informed our study and system design. So our system includes three hardware components and supports both PCVR and standalone operation. In PCVR mode, each hardware component connects to the PC. So the headset we use is a commonly available MetaQuest 3, and the core interaction hardware consists of two custom systems, a joystick system and a pedal system. The joystick system uses a rigid support structure to hold the two industrial joysticks in a stable configuration. And the pedal system replicates the real excavator pedals, which cannot be used directly due to their hydraulic mechanism and physical constraints. We built a custom 3D printed structure with a sensor at the pedal's rotation axis to measure pedal inclination. And on the software-wise, the soft simulator is built in Unreal Engine. We use engine features such as control rig, plugins like input mapping context, and custom classes for simulation and interaction. We use the Peak System SDK for campus communication between the joysticks and the PC, and Arduino reads and calibrates the pedal signal sensor via the Arduino IDE. We use Blender for modeling and animation assets. So for content creation, we started from the manufacturer's CAD model, removed non-essential parts, backed 4K materials, and retopologized the mesh for runtime performance. We also recorded real excavator audio at different engine speeds. For physics, a walking excavator combines aspects of robotic locomotion and heavy machinery, so standard vehicle models are insufficient. We implemented a custom spin damper ground interaction model. The wheel normal force is computed from the penetration depth, and we use an empirical tire force model. For runtime evaluation, the simulator runs at 72 FPS with baked light map and around 50 FPS with looming global illumination. Using an event-based camera, we measure the input latency of the controllers and the pedals, 92 milliseconds for the joysticks and 135 milliseconds for the pedals. With this training simulator, we are able to climb, but to reduce complexity and to support progressive learning, we designed multiple tasks and two user studies. So in the first user study, we investigated the impact of perspective. The FPV and TPV are standard perspectives, and the third setup, mixed perspective, included here a TPV display and a miniature excavator model for post observation. We used three tasks. Task 1, driving, including steering and obstacle avoidance. In the second track, the users must lower the undercarriage arm to reach the destination. And task 2 is cone reaching, where the users reach as many cones as possible within a time limit. The task 3 is a combined task integrating both driving and also cone reaching. We use a counterbalanced study design. For the first two tasks, participants would complete an exercise phase and a test phase. The test phase is always conducted in PV to assess the learning outcomes consistently. The task 3, which uses a mixed perspective, was always performed at last and evaluated mainly via subjective measures. Each participant would complete 5 sessions, and the study lasted about 1 hour for each participant. For the study results, objectively, more participants completed the driving task in PPV, and they traveled shorter distances, indicating a more efficient movement. For cone reaching, we found no clear difference, likely because the targets are fully visible in FPV. Subjectively, participants preferred FPV over TPV, and the mixed perspective received the highest ratings for lower mental load and better situational awareness. Then in the second study, we explored passthrough as an augmented virtuality aid for learning the special controller. We implemented passthrough as a 2D portal disk facing the user, so it initializes from the hand transform and then snaps to the controller position once the hands settle. And then it would update based on the controller main axis values. To evaluate its effect, we run an input following task using a real controller. Participants would follow randomly generated input sequences shown on the virtual slate. In the baseline condition, we used an animated virtual controller with all buttons and axes visualized in Blender via the shape keys animation. Participants would repeat the inputs with either pass-through or the animated controller as visual guidance. The results here show that participants would make fewer errors and also reported higher confidence with pass-through. Task speed converged after around 7 rounds. This is likely due to the familiarization with the controller and task. However, the effect was significant still in the early rounds, where the learning support matters most. To summarize, we developed a VR-based walking excavator simulator and conducted two user studies. Study 1 suggests that while TPV supports post-observation and navigation efficiency, users still prefer a realistic in-cabin FPV or a mixed perspective. Study 2 shows that our adaptive pass-through design supports controller learning better than an animated baseline, especially early on. In future work, we plan to test more complex climbing tasks and validate simulator behavior against real excavator measurements. Thank you very much for your attention.